exercise 1.1, first question, third and fourth. We have to decide whether these are reflexive relation, symmetric relation and transitive relation. So for the third one, we proved it is here xx belongs to R. Third one, xx belongs to R for every x belongs to A. Because x minus x is, since x minus x is, since x minus x, sorry, x is divisible by x. So for every x belongs to A, xx belongs to R, since x is divisible by x. Now therefore R is reflexive. Therefore R is reflexive. Now symmetric property, we can check the symmetric property. See, we know it is not symmetric. XY, ordered pair XY is an element of relation if Y is divisible by X. Second element is divisible by X. See, we know here 1, 2. 1, 2 is element of R. Ordered pair 1, 2 is an element of R. Since 2 is, see, if Y, second element is divisible by first element, then XY belongs to that relation. Here, say Y element, that is 2. 2 is divisible by 1. We know 2 is divisible by 1. So 1, 2 is an element of R. But 2, 1 is not an element of R. Since 1 is second element, 1 is not divisible by 2. So here directly, since it is not symmetric, we can show with one example. So here 1, 2 is only, you have to write 1, 2 belongs to R, but 2, 1 does not belong to R. Therefore, R is not symmetric. So only you have to show one example if it is not symmetric. Now next property, transitive property. See here we know it is transitive. So we have to prove it generally. We can prove. That means in the, what is transitive relation? If AB belongs to R and BC belongs to R, then it implies AC belongs to R. So we have to show that. So consider AB or XY. We can take XY, YZ like that also. So if XY belong to R and YZ belongs to R, implies. So this is the property. If XY belongs to R and YZ belongs to R, we have to prove that XZ belongs to R. So if XY belongs to R means what is the property of element of R? XY is an element of R if Y is divisible by X. So we can write, since XY belongs to R, we can write Y is divisible by X and Z is divisible by Y, because both these are elements of R. So we can write, this implies, we can write Y is divisible by X and Z is divisible by Y. Since XY belongs to R, Y is divisible by X. And Z is divisible by Y. Now divisible means what? Y is divisible by X means what? Y equal to some natural number into X. See, all the elements are here natural numbers. 1, 2, 3, 4, 5, 6. So we can write, if Y, that implies Y is divisible by X. That means that implies, we can write, so Y is divisible by X means Y equal to some natural number into X. So Y equal to some A into X. So if Y is divisible by X means, see, we know 10 is divisible by 5. So we can write 10 equal to 2 into 5 like that. Here Y is divisible by X. That means Y equal to some number into X. So Y equal to AX, and here Z is divisible by Y. So we can write Z equal to some number into Y. That is Z equal to some B into Y, where A comma B is an elements of are elements of natural numbers, set of natural numbers. So we can write, if Y is divisible by X, we can write Y equal to some natural number into X. And Z is divisible by Y means Z equal to some natural number into Y. Now that implies, we can write Z equal to, see in this value of Y equal to AX. We can substitute here. So we get Z equal to B into In the place of y, we can write ax. b into ax. That implies z equal to some AB or BA. BA into x. That we can write some numbers, natural numbers. B and A are all natural numbers. So BA into x. That means what? Z equal to some natural where ABA, where BA is an element of natural numbers. So that means Z equal to some natural number into x. That means what? Z is divisible by x. Therefore, we can write Z is divisible. Z is divisible by x. That means what? If Z is divisible by, what is the condition satisfied by the elements? Second element is divisible by x. Y is divisible by x. So if Z is divisible by x, what we can write? Therefore, we can write xz. Xz is an element of R. So we proved that xy belongs to R. Left side where we started, xy belongs to R and yz belongs to R implies we got xz belongs to R. That is the property of transitive property. That is, if xy and yz are elements of R, then xz should be element of R. Then we can say it is transitive. So we proved that xy belongs to R and yz belongs to R implies xz belongs to R. So we can say therefore R is transitive. Therefore we can write R is transitive. Transitive. So to prove if it is transitive, we have to prove generally. If it is not that, we can show with one example. Now, so that is over. Now fourth one. R in the set of, R is defined in the set Z of all integers, set of integers. R equal to set of all ordered pair xy such that x minus y is integer. Not that here it is defined in set Z, integers, set of integers. So here x and y are elements of set of integers. X and y are integers. So if x minus y is integer, xy, ordered pair xy belongs to the relation R. So we have to prove that it is, we have to check whether it is reflexive, symmetric and transitive. So here, see we know xx, we have to check whether xx belongs to R. If xx or AA belongs to R, then for every A belongs to A, then we can say it is reflexive. So here we can check xx when whether xx belongs to the relation. We know x minus x always is an integer. X minus x equal to 0 for every integer x. X minus x equal to 0, which is an integer. Therefore xx belongs to R. So it is reflexive. So we have to prove it generally. So we can write xx belongs to R for every x belongs to Z. See here in the place of A, set, it is defined in Z. This relation is defined in the set of integers Z. So first element, second element are element of Z. So when you write, you have to be careful. So here for every x, here x belongs to Z. For every x belongs to Z, xx belongs to R. Why we can say that? Because x minus x, what is the condition for xx to be in R? That is x minus x is integer. That is a condition. So a reason we can write, since x minus x equal to 0, we know for every integer x is any integer, x minus x equal to 0, which is an integer. 0, which is integer. Therefore, that is a reason for this belongs to R for every x belongs to Z. Therefore, we can write R is reflexive. Therefore, R is reflexive. Now, check the symmetric property. If xy, we can start with xy belongs to R, implies, we know by definition, what is our definition of xy belongs to R? X minus y is integer. So, this implies x minus y is integer. That is the definition, by definition. That implies what? We know if x minus y is integer, y minus x is also integer. So that implies y minus x is integer, that we know. So if x minus y is integer, y minus x is also integer. So if y minus x, see what is the definition? X minus y integer means xy belong to R. So y minus x is integer means what belongs to R? So what we can write? That implies what? Yx is an element of R. Because y minus x, see x minus y is integer means xy belong to R. So y minus x belongs to R. Y minus x is integer means yx, ordered pair yx belongs to R. So we prove the condition. See xy we got xy belongs to R implies yx belongs to R. That is the definition of symmetric property. So from this what we can write, therefore R is symmetric. So we proved R is reflexive, R is symmetric. Now we can prove the transitive property. What is transitive property? We have to start xy belongs to R and yz belongs to R implies. So we have to start with this. Xy belongs to R and yz belongs to R implies what? Xy belongs to R means what? X minus y is integer. Yz belongs to R means what? Y minus z is integer. That we can write by definition. So we can write that implies. Here we can write x minus implies x minus y is integer and y minus z is integer. So we can write x minus y. From this we can write x minus y is integer and yz belongs to R means we can write y minus z is integer. Now that implies what? See, if this is integer, this is integer. So we know sum of any two integer is again an integer. Sum of two integers is an integer. Therefore what we can write? X minus y plus y minus z. X minus y plus y minus z is integer. So from this we get x minus sum of two integers is integer. Therefore x minus y plus y minus z is integer. So we can write what? Minus y cancel. So x minus z is integer. So we got x minus z is integer. From this by definition what we can write? X minus y is integer means xy belong to R. So x minus z is integer means what? Xz belong to R. So what we got? Xy belongs to R and yz belongs to R implies xz belongs to R. So R is transitive. So we prove R is transitive. Okay.